Comparison of linear unmixing methods on painting datasets.
Yes.
In English, I guess.
Yes. Okay. Good morning, everyone. Can people in there hear me? Okay. So today, what I'm talking about is the comparison of linear mixing methods on painting dataset. So as you see, my main supervisor's quality boost. It's in CTRMF in Paris. It's the Centre de Recherche Restauration de Musée France. It's an institute that doing the research about all the all the paintings, all the cultural heritage in the French museum. So mostly I stay in Paris, and also I have several co-supervisors from UBFC, which is in Dijon. Also, I get another supervisor in NTNU in Norway. So let's get to our topic. So today my presentation will include 4 parts. They are respectively introduction, methods, experiments, and conclusion. So let's get into the first part. So introduction. So we know the hyperspectral unmixing. For the hyperspectral unmixing usually, there will include 2 important parts. They are separately first we need to extract the spectra, which we often call the end members, and after we extract the end members, we need to estimate their respective the abundance, that is to say the proportions of each parts. So even though in the past few decades, especially in the field of remote sensing, the hyperspectral mixing and this end member extraction methods, they have been applied in various fields, include the rock and soil classification, vegetation detection, crop yield, but its relevant application in the cultural heritage, especially when we talk to the paintings, are relatively few. So okay, so this formula here, the y equals the e. The E multiply A plus the epsilon. So here you can say that the Y here is the hyperspectral image, or the whole data set we get, and the E it denotes the end members, and the A is the abundance of this of all these end members, and the epsilon equals the noise. So the problematic. As I had mentioned just now, so even though the hyperspectral unmixing has been used for the past few decades, and its application is very various, but as you can see here, the relevant research on the paintings that are very few. In fact, only in the past few years, in the last year, the 2020, and this year, the 2021, there are some newly published works about combining the hyperspectral mixing and the image part. So in this paper, we mainly adopted 3 methods. That's VCA for text component analysis, NMF, and NFinder. So the reason why we choose these 3 different methods, because these 3 different methods, they are already being widely used in the remote sensing field. So that's to say, somehow they are recognized as the methods robust, and we choose them 3 is because that they are different from, they are based on different assumptions and constraints. Briefly speaking, so the n finder R is to treat that since there are n end member. So for the n dimension, the value is to find the end member that can form the biggest value of the simplex. And anyway, so because they have different assumptions and constraints, that is to say, on different data set and on different real cases, they may perform differently. So that's better for us to compare. So now we come to this data set. So this data set, in this data set, there are 7 pigments included. So as you can see here are in total there are 175 color patch. So for each color patch is the 2 centimeter multiplied 2 centimeter. So in this data set, for each color patch, there are 3 possibilities. Either they are just the pure of one of the 7 pigments, or they can be a mixture of 2 or 3 different pigments. So some of you may ask, why the maximum here is 3? Because usually in real cases, I mean in real paintings, according to the specialist in the according to the idea from the specialist from the conservators, usually the maximum number of the mixture in painting is 3. So that's reason for the number here. So here is to show that the 7 pigments concerned. And here you can say that the horizontal is the wavelength from 400 nanometer to 1000 nanometer, and the vertical one is a reflectance. So in this data set, the ground truth we already know is that we have the spectra of all the 175 color patches, and we know the corresponding abundance. We know the ground truth correspondence abundance for each color patch, and we also know, like here you can see the reflectance of each of the 7 pigments. After we have decided our methods, we need some metrics to evaluate how the results are. So here we mainly take the three methods. They 3 metrics. They are respectively SAM, SID, MMPE. So briefly speaking, the SAM is more to evaluate the angle between, or we say it's more to evaluate the direction of the spectra, while the SID is mainly based on the cross entropy, and for the last one, the MAPE, we adopt it because its result will be presented in the form of the percentage, which is very intuitive compared to the SAM and the SID. So here, here we show here in the fig, you can say for each one, the one in the right, it shows the result for the between the extracted end members from VCA, NMF, and NFinder, and the ground truth. The ground truth one is the blue. So here we can say that the result that these 3 different end member, these 3 different method extracted and member with the ground truth one. So among the seven end members, the ultramarine blue we get the best performance, and in the right one, for the pigment of the cadmium, it gets the worst performance. And okay. So in here you can say from the metric of MAPE, it's very intuitive that that some for some pigments there exist some extreme values, especially for the VCA, because you say for the hammer white it's even the it's even more than 200%. So to analyze this reason, so here we use another metric. This metric is short for SAVD. That is to say that for each color patch, for each color patch, we need to to calculate the sum of the absolute value between the seven potential pigments. So in other words, the SAVD is a metric to evaluate the performance of estimating the abundance of each color patch. From the definition of SAVD, we can say that if for a color patch, when its SAVD is smaller, that indicates that the abundance estimation is better, and vice versa. So here is that we can see the result. So one thing interesting here to point out is that, for example, when you see the fig in the top left, you say that except for the VCA, NMF, and Finder R, there are another two. The blue one is the reference. The red one is the theoretical spectra. So this is because that even though in this research, in this paper so far, we adopt the linear the linear method, like we can say anyway. So like we can say before, we assume that the relationship or the contribution from each pigment, their relation is linear. But in fact, especially for the oil painting, it has somehow already somehow be demonstrated by other research. They are more likely to be non-linear. So okay. So here that in this table it shows that it shows that for the four color patch in the former slide, the estimated abundance from each method and their difference with the theory part. So yeah. So we can notice that at some cases, like for example, for the color patch 94, we notice that the estimation of NMF is somehow outlier. So it's because, as I mentioned, it's because because in fact there are some interaction between the different pigments, but so far we assume that so far the model is to assume that there is no interaction between them. And also, here you can say that there is no constraint on the pigment number during the last step of the end member extraction. But as I mentioned before, so usually in the real cases, the maximum the maximum number of the pigments in the mixture, the maximum is around 3. So that's the reason for this table. So conclusion and future work. So I think for this one, the most Okay. I think for for this one, this is like what? This is like the first paper of our series, because in this paper it has proved the possibilities to apply these methods, which are originally in the field of remote sensing, into the field of the painting. So this is what other researchers haven't done, and yes, we have to admit that its performance, even though its performance in end member extraction is good, but its performance in the last step, in the estimation, in the abundance estimation, may not be that good. But yes, I mean, this is what we will improve in the future work, because the next step will come to the nonlinear model, and we'll think about combine the Kubeck-Monk and maybe the deep learning part, and yes, and for the future work, we'll also create a painting data set with the larger volume, and because in this data set, its proportion is somehow fixed. I mean, if there are, if in the pigments, if in the mixture there are 2 pigments, the proportion is one versus 1. But in fact, in real cases, its proportion can be very varied. So that's what we will improve in the future. So basically, something like this. Thank you.
Questions? Des questions? No? Plus?
Do you have a problem with stability in time of the pigments? Maybe the reflections.
Oh, okay.
Spectrum is varying in time?
Okay, I understand your question. Your question is that saying that if a painting is very long, like hundreds of years, that is likely that the pigment will decay, which will affect like the reflectance, something like this. In fact, yeah, this is a good question. But in fact, so far, like the data set I have in hand, and I will get into, it's about the French painting in the 18th or 19th century. So yeah, I understand your concern. It's a good question, in fact. But so far, if we deal with the painting, that the time is not so long. So the variation, the change, that is not so apparent. So that's okay.
Okay. Other questions? So I think we will move on to Jean-Paul, so we can try to more or less keep the timing. And we thanks